So I've talked about all of the stress models and strain models, and remember yesterday I said there's always three ways of looking at things. We can look at nucleation or the stress approach, or microcrack approach, which is the strain approach, and finally there's macrocrack approach. So I'll talk a little bit about the fracture mechanics models. But because it's after lunch, I always have to put in something to help get ready. And so I thought I would show you about my house. Fracture mechanics. Yeah, so this is a picture of my house.
Nice stuff.
Over there someplace. Yeah. Yeah. This is what I do. I build all these kinds of structures. So I got a book about the traditional and the ancient Japanese techniques for making buildings, and I thought, oh, this would be interesting. And so I built these structures. These structures have no glue and no nails and no screws. Only from the ancient way that they have the old temples. And yeah, if you look at this, then all of these pieces fit in some tapered slots. And if you look at a 500-year-old wooden building, an old Oriental building, the building is stronger with time, because the more the building moves like this, then the tighter and tighter the joints become. And so I became fascinated with that, and decided to see if I could do all of that. And yeah, it was great fun. I made all of this only with chisels, all by hand.
You did it with your hands.
All by hand. Yeah.
Respect.
Yeah, I would rather do this than engineering. But unfortunately, I can't make enough money to support myself to buy all of the things that are needed. But I would rather do this. Yeah, it was great fun. It was great fun to do it. But the old joints were very good. Very good. They're very, very intricate and complicated. And I say, so the more it moves, the tighter and tighter and tighter everything becomes. So it took me maybe 4 or 5 months to make all of this by hand. And because I thought it might be a hot day, this is my garden in the wintertime. Maybe we could use some of this snow today. When it's very, very hot. I like to point out about this piece. Okay. So this is a Japanese lantern that I got in Japan. So I visited with my friend, Professor Murakami, and I told him that I want to have a Japanese lantern. And first response always is, it's difficult. And if you're a very polite person, then you don't ask again. But I'm not always polite with my friends. So I asked again, and so we went and we got this lantern. And so now I have a lantern that I bought in Japan that I need to my house. So he said, it's no problem. So the lantern was shipped to his laboratory, and on the outside of the box he marked ceramic test specimens and shipped them to me. And maybe 2 months later, then this box arrived at our laboratory. And the man at the machine shop calls me and said, oh, there are some special test specimens from Japan that came, but they came in a very big box. What should we do with this box? So of course I said, oh, please don't unpack this box, but just put it in my laboratory. And I ended up with, it was great fun. It was great fun. All right. So we just think about the fracture mechanics models for multi-axial loading, and what they tell us and what they might do. And so, of course, we have to deal with the 3 different kinds of loading. Mode 1 is the most common. Mode 2 is the in-plane shear, and of course, Mode 3 out-of-plane shear. And the behavior in these modes is quite different. And we have been talking about this for small cracks. Right, what happens, and I've been doing this with my hands. So let's look at what happens now for bigger cracks. Right, cracks bigger than a millimeter. So first thing, well, we can look at this a little bit about the plastic zones. And so if we set up a crack in a plate, of course we can load it in two different directions. We can change the ratio of loads that are here. We can incline the crack at different angles. And we would like to know the behavior of these kinds of cracks. So first of all, a little bit of the mechanics. Right? I thought after lunch you need to spend some time with the equations. So, sometime when you're not busy, derive these equations. Not today. But you know, if you look at all of these equations for biaxial loading, they look very much like the standard fracture mechanics equations. And for a particular crack that is given the load, and of course you have a crack length, that it really depends. All of the stresses and strain depend only on the ratio of the loads and what the angle of the crack is. Right? Everything else is set by basic fracture mechanics, as it is in a uniaxial loading case of a crack. Right? A uniaxial case of a crack, everything is set by the theory of elasticity equations. Anyway, we just use those and do things and just look at the differences in plastic zone. Because maybe we have a notion that the plastic zone size should be related to how fast a crack can grow. And that if we have small plastic zone sizes, then the crack will grow slowly. And if plastic zone size is very big, then the crack should grow much faster. And so you can see what happens is that the growth of a mode 1 crack. So a mode 1 crack can grow in shear loading. What do I mean by that? So I have this load, and I have a principal stress that's here, and I have another principal stress that's here. And this crack is growing along this plane in mode 1. It's different than a shear crack growing in torsion. Right? This is really torsional loading. If I twist this, I'm really shearing this across this way. Okay? And that's, of course, when lambda is equal to -1. There's lambda is equal to 0, and lambda is equal to +3, right there. So plastic zone grows as you add the second component inside. And I will contrast that in a minute, what happens with mode 2. Right? So here's that picture, and here's what happens for mode 1, just by introducing the shear loads, and here's the plastic zone, and here's another crack off at 45 degrees, and here's the plastic zone under the same stress system. So if you have a mode 2 sliding displacement, the plastic zones are huge. They are very, very big compared to the corresponding mode 1 plastic zone. And a material can choose how it wants to fail, and we know from our experience it always changes from this to this. Right? If I really have this crack in the structure, this crack is always going to change from trying to grow in mode 2 into mode 1. Maybe the natural world wants to have the lowest energy. So why not pick this other mode that doesn't require so much plasticity? Maybe this is the reason that these torsion cracks always turn. I'm not sure. So this is the mechanics of it. Right? Now, if you go into literature, you will find that there is very little work on fatigue crack growth under the other modes of loading or any kind of combined loading. And one of the problem is illustrated here. So here's data about the growth of a mode 1 crack as you change the loading. And so lambda equals 1 is biaxial tension loading. Lambda equals 0 is uniaxial loading. And lambda equal -1 is the shear loading, but on a tension plane. And here's what the growth rates are under those 3 modes. Hardly any difference. Hardly any difference. So maybe this difference is only a factor of 2 in the growth rate. Well, if there's not a large effect, chances are there's not a lot of research. If you increase the stress levels, if you double the stress levels, then you can start to see some differences in the growth rates, but that's only as you go to stress levels that approach the yield strength of the material. So now you have net section plasticity concerns. So I think it is safe to say that if I look at mode 1 growth, just mode 1 growth of this crack, just mode 1 growth, this stress doesn't matter. And there's almost no research anymore in this area. This stress for the growth of a mode 1 crack doesn't matter. So all of the effort in fracture mechanics modeling is into other modes of growth, mode 2, or the growth of a slanted crack in how it turns into a mode 1 crack. But the growth in a mode 1 crack, there's no effect of the so-called T stress. So let's look at some of these others. And that is, of course, in torsion, you get two different types of cracking. And if you have a bar in torsion, you can have a crack which goes in on the surface like this. Of course, because in a bar in torsion there's always a stress gradient, this crack tends to grow along its length more so than into the depth. Or you could have a circumferential crack like this. This crack is growing along the surface in mode 2, and it's growing in the depth in mode 3. And this crack, a circumferential crack, is always in mode 3. So in shear loading, let's look at the growth rates. And the first thing to note is that if you give me a bar that has been tested in torsion, then I will tell you what the fatigue life is. Just from the broken bar. How can I do that? You know, shear loading is unique in that depending on the lifetime, you get very different fracture modes. If you test something at a very high stress level, not very many cycles, right? So I just twist this and so on, not very many cycles, then the failures are always transverse. They start and they just grow across the specimen like this. Just like twisting a static failure. And if I decrease the stress level some, and again do the same torsion test, now the failures all run along the length of the bar. And then finally they grow into the depth. And this is the intermediate regime. And so I call this the longitudinal fractures. And finally, if I have a torsion test at a very, very long life, the cracks always nucleate in shear, and then they turn to grow into mode 1, and they spiral around. And this is always the order of failures. The failure mode is very different with stress amplitude. And you get to 3. I'll show you some examples. It's also a function of material, and of course most of the data is in steel. This just quantifies what I just said. If you test at a low enough amplitude, of course you never get cracks. It's a long life, these spiral cracks, these longitudinal cracks, and then finally the transverse cracks at really high stresses and short lives. So that's what we observe. How about growth rates? So you have to search to find growth rates in other than mode 1. And I have three or four different ones. Most people want to know, is the growth rate of a mode 2 or mode 3 crack larger or smaller than mode 1? Why do they want to know that? Well, all of our materials data comes from mode 1. And I want to use that to predict what will happen in some other mode. And I just want to know, is it faster, slower, or about the same? And so most of the data that you find always shows that the mode 3 crack growth rate is an order of magnitude slower than mode 1. Well, if that's a slower mode of crack growth, then it's not a surprise that a material would try to turn and change direction and go from mode 3 to mode 1 if it can. And that's exactly what you find in service. I'm going to come back and talk about the mode 3 growth again in a few minutes. Here's just even more data, and you can find anything you want in the literature. So if you build a new model about long crack growth, and you want some data to show your model is correct, you can find it. Doesn't matter what direction your model goes, more or less, and so on, because there are very few careful experiments. So here you can see, well, okay, I've managed to find some data that shows the mode 2 and mode 1 growth rates are about the same. And then I find from the same author, I can find that the mode 2 growth rate is actually less than the mode 1 growth rate. And I can find data that shows the mode 2 growth rate is greater than mode 1. And so what I hope I have done in the last few minutes is to paint a very confusing picture, right? Because it is. And the reason being is that people haven't done the careful experiments. Because you know, for the last half a day, I have been standing up here and I have been showing you, look, these sliding modes, either modes 2 or mode 3, and we talked about the effect of some friction that tends to open and close those cracks has a really big effect. Right? None of that's reported in this data. None of that's reported in this data. So let's look at what really happens. Let's look at what really happens. And by the way, there's no shortage of models, right? That probably took me 10 minutes to get the different models that people proposed without experiments. And you can see there's just all kinds of stuff of trying to get an equivalent next to it. I think that's a waste of time. So I want to spend the time talking about these models. What happens to a long crack? What are the important variables? So first of all, let's just look at testing something in torsion and in bending. So I just take a solid bar, and this is a bar in bending, right? So I have a bar in bending, I'm going to bend it back and forth like that, and I'll get some life, maybe a few 100,000 cycles. And this is what I see on the surface of the fracture, on the fracture surface. Of course, if I have a bar that's in bending like this, and the bar in bending, then of course the crack will nucleate here, and this crack will grow towards the center, and because it's in reverse bending, then a crack will nucleate here, and it will go through the center. And we know about how to calculate the closure loads and openings and so on. But it's a very well-defined flat fracture surface. Okay? Fine. Fracture mechanics works more like this. All mode 1. The only difficult part is to look up the stress intensity factor for a crack that's in a curved shape. Okay, that's the only hard part. Let's look at just twisting this now. I take the same bar that we had in bending and now twist this back and forth. And when you look at the fracture surface, right, this is what you see. Right? Nothing planar like this. Right? When you look at the fracture surface, look how irregular this fracture surface is. Right? Think about it, when this fracture surface is very irregular, then I have a lot of, right? I have a fracture surface that looks like this, and I have a lot of mechanical interlocking. So almost all of the force is taken out by mechanical interlocking, not driving the crack. Well, what is the stress intensity for this? How much of the applied torsion is effective in growing the crack? That's the primary variable. So let's look at that a little bit. So I make a little cartoon of what happens. So this is what a crack really looks like. Right? When it tries to grow. And this is on the surface of mode 3. Some people describe this as a factory roof fracture. So you can imagine this part looks like the roof of a factory. More or less. Right? But how, and this crack is trying to grow into the depth, and I shear this back and forth. Think about the mechanical interlocking that happens. And if you don't like this picture, then think about all the friction that must be there. So quantifying the friction is very important. And then think about that if I really have fatigue situation that's cycling back and forth, then I will also generate a lot of wear debris particles because of all of this friction and all of this interlocking. And so this creates even more debris. Right? This is the essence of understanding modes 2 and mode 3 fracture. This interlock. Okay, let's look at a few other things that happen, right? Just to try to compare the behavior in mode 3. By the way, that kind of interlocking is unknown in mode 1, right? There's no concept of this interlocking, no concept of that kind of friction, or no concept of the debris in mode 1. If we look in mode 1, then of course if you have a tension overload, then what you find is we're growing with a constant growth rate, and of course after I have a tension overload, then I introduce these favorable residual stresses in front of and behind a crack, and the growth rate decreases by maybe 2 orders of magnitude, and then as the crack continues to grow very slowly, it slowly recovers to the normal growth rate. And that's our expectation in mode 1. How about mode 2? What should happen? So we have this general idea. Overloads cause crack retardation. Right? All the fatigue people know this, right? It's the basis of safely flying on an airplane. From time to time, the airplane will be overloaded and it will arrest the cracks. I know this to be true. So on Thursday when I fly home, if I notice a crack in the wing, my job is to convince the pilot to do a loop with the airplane so that he puts on a large tensile overload on the wing, because I know from my observations in the lab that a large tensile overload will arrest the cracks. I know this will work, but I doubt I will be successful. First of all, it would be difficult for me to get anywhere near the pilot these days. When I walked up to the front, someone would be there to meet me. But, okay, well, how about these other modes? What will the effect of the overload be? What do you think? Let's go back to our model. So here's a model of the kinds of physics we want to deal with. And what would happen if I put on a very, very large load so that I had very, very large twisting displacements?
It would make things worse.
What?
It would make things worse.
Make things worse. How many think worse? Okay. A few. How many think better? Not a single one. How many don't like my quiz questions? You know, when I teach, the students never like my quiz questions, because I never give quiz questions like the homework. You know, I know they know how to do the homework problems, right? So I ask these very simple questions. Very simple, worse, better, and so on. Well, you know, it turns out that it actually does make it worse. Just the opposite of tension loading. So remember, tension overloading arrests the cracks. But let's just think in our mind about the physics. Suppose I had this situation, right? I had all this interlocking, right? If I put on a very large torsion cycle, a very large mode 3 cycle, it would tend to flatten this surface, wouldn't it? And reduce the surface roughness, right? Because I'm putting on a very large cycle, right? Or here, right? The reason we have friction is this is in a regular shape. So that would cause that, make the cracks go faster. And the same thing here. So this is our idea. How about the experiments? What did the experiments show? No, we have to look. Worse, right? Because after you apply an overload in torsion, right, you can see that the growth rate actually increases. And then it goes back to the growth rate. And what's different about these, this is overloading 50%, 100%, and 200%. And you can see the amount of acceleration in crack growth depends on how much twisting I have, because I'm changing the crack face friction. I'm changing the crack face friction. And that has more to do with the growth rate than anything else. And here's what happens if you forget about that. we have this idea that we can go find some data in the literature. So here is some very nice data for mode 3 crack growth. Very carefully taking data and so on. And we have this idea that there's a unique relationship. We say, fine, I know the growth rate looks something like that. So there's a one-to-one correspondence between stress intensity, and we can let this be modes 2, or we can let this be mode 3 if we like, and so on. And not at all true. Right? Not at all true. Let's just look at this data. So here's the crack growth rate. Very careful experiments. And these are done at different values of constant delta K. So here are the values of delta K, and look what happens. So here is the crack length out to the first millimeter. And so these start off with the stress intensity. So for example, the circle stress intensity of 15. And look what happens. I start off and I maintain the stress intensity constant. And okay, it grows pretty fast, but look, as the crack starts to grow and grow and grow and grow, the growth rate becomes less and less and less, and it's changed now by at least an order of magnitude. And why is that? Oh, you know, when the cracks are really small, there's not so much friction. But as the cracks grow larger and larger and larger, then the fracture surface becomes more and more irregular, so I build up more and more friction, and so the cracks keep slowing down. Right? And then, well, let's just look up here, right? Delta K of 10, right? Just make it smaller. Okay, it starts off, and the growth rate is here, a little bit slower, but look. 1 order of magnitude, 2 orders of magnitude, 3 orders of magnitude, just because of building up these friction forces. Building up the friction forces. So most of the mechanics models are useless. Right? Because they don't get the primary rate. And how do you calculate the friction? No one knows. There are no good friction models. It's a very, very interesting and important research area. Very, very, very interesting. There are some things people do, however. Right? I mean, that's the real problem in torsion. There's a lot of work done in these kinds of problems. And these are problems where somebody looks at a plate with an inclined crack in it. I don't know how useful that is in a real situation, but it's easy to study analytically and experiment. And this is the best data, and you can see where it comes from. And Suka has the idea that cracks try to grow either in tension or shear, and so you can see why I am attracted to this work. And depending upon the orientation of the crack angle here, then you can get different orientations of mode 1 and mode 2, so we just plot K2 and K1. And what you actually find is, of course, when these values are small, nothing happens. And then you can have a region for which you always get growth in shear, right, at the very low stress levels. And then as you go to higher stress levels, then you always get growth in tension. And his ideas are, if I want to know if I have tension or shear growth, I calculate a tension and a shear stress intensity. Basically, I can work out the stress intensity factor in any direction that I like, and so I work it out in the direction of the maximum principal stress, and I work it out in the direction of the maximum shear stress, and from that I can tell what the expected growth direction is. There's also a lot of people who worry about mode 2 and mode 1 thresholds. They suffer from the same problem of this shear closure force. If you want to know the threshold in mode 2 of a tensile of the standard test specimen, it's easy. But transferring that to any other knowledge is not so easy because of the changes in crack-based friction. And again, you see the same kinds of ideas for threshold stress intensity as you do for long crack growth. Plot K2 here and K1 here, a region where nothing happens, a region where you get shear cracks, and a region where you get tension cracks. And then, of course, there's some modeling, right? That's done. You may need this. You may need this tomorrow. You start out with an angle crack like this, and you try to predict what the crack path is as it grows. And there are a couple of ways that people try to do this. Right? And the most useful one is the strain energy density criteria. This is by Shi. And you essentially calculate a strain energy density, and well, there are the formulas for doing it. It's combinations of the stress intensity in mode 1 and mode 2 for these ones. And if you want a crack to grow, then you simply look at where's the maximum strain energy density, and the strain energy density will change as the crack grows, and you make predictions like on the last slide. Yeah. So I never spend much time on this section. And I do that deliberately. This is an area that has hundreds of theory papers. Hundreds of them. Right? And maybe 20 papers with data. Maybe 20. There's just very little experimental observation and backing up in this. And so it's an area that's very fruitful for research, I think. But there are no guidelines and no established techniques, and you have things like I showed you on the mode 3 growth, right? You know, it's so dependent on the friction that's there. But it's just a really nice area. So I stop here. I don't have an opinion what is the best model, right? The only opinion I have on all of this is my observations are cracks grow in either mode 1 or mode 2. Or mode 3 in torsion. I've never seen a crack growing in mixed mode for very long. Right? Cracks always try to either stay in mode 2 or they try to grow in mode 1, and they never grow at some combination of mode 1 and mode 2. They always move towards one or the other. That's the only observation I would make. So I always stop here, having given you an idea of what's happening in the fracture.
Sorry?
Yes.
You say you've never seen a crack growing in mode mixed.
Yes.
That will depend on the material. I mean, are you talking about metals?
Yeah, a big crack, yes.
Okay.
Yes. A big crack in metals doesn't grow in a mixed mode.
So metals. But
Yeah.
what if we talk about like composite materials or other stuff like
A
that?
crack will grow along the interface.
Or like the... Well, because I'm working on this. I'm working
Yes.
on mixed.
Yes.
With the crack growing in foam core, or these very low density materials.
Yes.
So do you think that's the same? Because actually, I'm making cracks growing quite long, but I don't know if they're growing under monicity. But maybe if you say it's a fake monicity, so that's mode 1 or mode 2.
I think that's what happens. The crack tries to grow.
One mode dominant. Like
Yes.
One mode.
Yes.
Yeah.
I think there's a dominant one.
Sure.
Yes.
Yeah, there is.
And if you go back,
Which one says
What?
slide number?
Yeah.
See, I'm learning Italian
Impressive.
slowly.
so let's look at the problem. In that the people who want to study mode mixity, then they make an angle of some sort. Okay, that's easy. But you know, a real crack is three-dimensional, even though we draw it like this. It's difficult to turn the corner here. Right? Well, how do I take a crack which is straight across like this and maybe curved like this, and I now want to grow off in another direction? And so what you'll find is maybe inside the crack is still trying to grow coplanar, and outside the crack is trying to turn. So on average, then you will find regions like this. And if I actually calculate what happens for the stress intensity solutions here, this is really growing in a mixed mode. But it's dominated by mode 1, and the tendency of this crack is to get over here so that it can be pure mode 1. Right? And so yes, there is a portion of life here where the crack is trying to turn. But that's hard, right? Because we like to analyze and we look at things only in 2 dimensions, and in 2 dimensions it's easy for us to turn the corner. But in the 3 dimensions of a real crack, not so easy. not so easy. So during that period, I think you'll have much more. That's true. Yeah. Thank you for asking questions.
Yeah. My Italian is not as good as it used to be. Oh, no, I want to go back to that. Oh, there. More study is needed on my Italian.
That's always the case, right? So now I want to talk a little bit about non-proportional loading examples. And I will talk about in-phase and out-of-phase loading and some non-proportional hardening and finally some variable amplitude things. So first of all, different kinds of loading. So I can think about taking this bar or some component, and I can load this with tension loads, and I can also load this with torsion loads. And if we think about loading these with a sine wave, then these sine waves can either be in phase or out of phase. And the frequent question is that if I load this, is in phase loading more or less damaging than out of phase loading? Because of course, if I knew that in phase loading was always more damaging than out of phase loading, then it would be easy always just to run in phase tests. Of course, if I knew that the out of phase loading was the critical load case, then it would be easy to run tests with that loading. So I'd like to know that. So what do you think? Is it better to have the loads in phase or out of phase? Which would be more damaging? So it will not surprise you if I answer the question with, I don't know. What?
Phase is worse because when you open the crack, you have more tension.
In phase is worse because when you open the crack, you have a lot more tension.
No, and you have also the
And shear. You have a lot of shear and tension.
The friction.
That's actually the correct answer for the wrong reason. Listen, if you think about these to scale, if I have two of these in phase, then with the maximum tension and the maximum shear at the same time, then the principal stress and maximum shear stress are bigger by 40%. Okay? Sure, I pull and twist at the same time. The maximum stress exists off of the plane 22.5 degrees, and the magnitude of that stress is 40% higher, right? Square root of 2 higher. So you are correct, the stresses are bigger, but it's actually the magnitude. Well, you know, sometimes you get the right answer for the wrong reason. And, you know, I give credit. You know, it's okay. You know, results driven. When I had my heart surgery a few years ago, I didn't care about the operation and how it worked and so on. I only wanted the physician to be successful and for me to feel better. And if he made some mistakes and I still felt better, it's okay. It's okay. I don't care if he used exactly the right techniques, but it worked. Actually, it worked very well. Before I had surgery, then I could only walk about maybe 50 meters, and then I would have to take a rest for a half hour. 50 more meters. And so I would go to my office in the morning, and after climbing up the stairs to my office, I would sit for about 30 minutes and then do a little bit of work and so on. Awful. Just awful. So, yeah. So I was very lucky to be able to have some surgery to correct this problem. Anyway, look, you do this out of phase, and out of phase, then when I have the maximum shear, then I have zero tension. And so the magnitude of the ranges are all smaller. Right, so given that information, is out of phase loading more or less damaging than in phase? So again, you're all apprehensive, right? But look, the ranges are 20%, 40% less, right? Square root of 2. 40% less on the ranges. So of course we would think that the out of phase loading is always much less damaging than in phase. And I will tell you sometimes. And that's what I'd like to explain a little bit. So let's look at what happens in an out-of-phase loading test. Okay. So the first thing is if we look at the stresses, and we look at those as a function of time, and so here is a complete cycle, right, one loading cycle. And if we look at the octahedral shear stress, then throughout the loading history, the octahedral shear stress is constant. Okay. So that means if I did something like use Sines criteria for the octahedral shear stress, and I had out-of-phase loading, it would always predict no fatigue damage, because the octahedral shear stress is constant. Never changes. That's the purpose of the out-of-phase loading, right? So that's probably not a good criteria. The maximum shear stress changes a little bit, but not too much. Right? It rotates in direction, right? But its magnitude never changes. If I altered the ratio of torsion to tension loads, I could make the maximum shear stress constant, and the octahedral stress would have a small sine wave. Right? But look, there's a big change in the applied axial loads and a big change in the applied torsion load. Right? The octahedral parts are zero. And this has been the problems in non-proportional loading. Many of the traditional models simply don't work because they use equivalent stress, which is not sensitive to the out-of-phase loading. Oh. And that just draws the two together that I have talked about. This is the out-of-phase loading path, this is the in-phase loading path, and this magnitude, as I said, is 40% larger. So I'm back to my quiz experiments. Right. So can we understand these concepts of out-of-phase loading? And so I want to make up 5 different loading paths. First loading path is an in-phase loading path just for comparison. Second loading path is an out-of-phase loading path of sine waves. Third loading path is an out-of-phase loading path of triangle waves, and so you get a diamond instead of a circle. And then you can have a square path, and then I can have a different kind of out-of-phase loading, one cycle of tension followed by one cycle of torsion. Okay? And if you want to see these loading histories, right, that's what they look like. So let's go back. Of these loading histories, which is the most damaging? All about the same. So I always like to ask you to do this because just to see what you, based on what knowledge you have learned, what your intuition is. Right? So you don't have to tell me, but think about what you think the order should be and why, because of course we will go over and look at a strategy. So, all right. Well, what should the strategy be? So what we built up over the morning is we built up a strategy that a good strategy for getting fatigue damage is, well, you know, the mechanism of fatigue probably hasn't changed, and so we worked a lot with my hands. Okay, ductile materials, we have these micro cracks which are sliding, and we have opening loads which tend to open those micro cracks and so on. So we have an idea of the physics in our mind. Right? We don't have a quantitative description yet, but we have an idea of the basic physics that we talked about. Will the physics be different for these kinds of loading paths? All right. No, why should it be different? Look, the crack knows nothing about the external loads. So I can think about the crack is going to nucleate somewhere on this page, and so let's just say that for whatever reason, this is the critical area that a crack will nucleate, right there. And this material knows nothing about how I load out here, right? Absolutely nothing. The only thing that this material knows is this material knows the stresses acting on it from whatever the source might be, and also the strain, right? From whatever the source might be. Right? So I have no reason to believe that the fatigue mechanism would be different, right? Because this material doesn't know. Right? So we still have this idea of, okay, we have some shear stresses driving the nucleation and growth of these microcracks, and we also have these normal stresses which tend to open up the cracks. So now I want to know from these histories, I say, well, okay, which of these histories has the most shear stress somewhere? It's not obvious to me. Well, it is to me because I've given the lecture before, but it was certainly not obvious to me the first time, but I have a strategy, don't I? I know that when I look at these loading histories, I want to look for combinations of shear stress and normal stress, right? And I want to look which of these histories causes the biggest combination, because I could have a scenario where in one case I don't have so much shear stress, but I have really big normal stresses. And maybe another history produces something with really big shear stresses and normal stresses which are not too high. And none of us can guess these things unless we've done it before, right? But that doesn't change our basic strategy and our ideas about. So there are the histories. So let's just go through these. And for reference, let's take the in-phase test. So here is the in-phase test, and just for doing something quantitative, then I choose Findley's model. Good enough. And I choose a stress state, tension loading to 500 megapascals, and I look at the shear stress for in-phase loading, and I look at the normal stress, and this is Findley's criteria, and so I combine the shear and normal stress, and this is the combination. And I want to know about the lifetimes, and so I just set that lifetime equal to 1 because I am interested in the relative lifetimes with this. And then I look at the 90-degree out-of-phase test. So when I look at the 90-degree out-of-phase test, when I look at this, then I immediately say, oh, the magnitude of the range must be smaller. Okay? True. The magnitude of the range is smaller. But in addition to the shear stress, there's now also a big normal stress. And you can think about the normal stress, that if this is the shear plane, the normal stress is related to the distance that's perpendicular to that. I can say, look, wow, that's a big circle. So this will have a big normal stress. And sure enough, you can see that the normal stress for this path is twice as high. Twice as high. So this is a little bit lower, this is twice as large, and if I look at Findley's criteria, it turns out to be here, and not very different. Right? Lifetime said maybe twice, 2 times in the lifetime. If I wanted to make them the same, maybe I could adjust this constant a little bit, make it a little bit less or a little bit more, but basically the same. Right? Who would ever guess this? And the answer is no. So the only way to think about interface loading is to do the calculations. Because none of us can think about how the shear and the normal terms combine. Well, let's go to the others. I happen to know that if I search this for critical planes, the potential critical spots are here, 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 and here. And those happen to be the same spots that are here, 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 and here. So the results will be the same. Now let's look at the square path. So on first glance, I look at the circle path and I look at this and I just change this from a circle to a diamond to a square. We might say, you know, there should not be very much difference. What difference does it make in the path from circle to diamond to square? But we'll find it makes a big difference. Why is that? This path is the worst of all worlds because it has the biggest range of stress, shear stress, which is this diagonal, just like this one. Okay. And at the same time, it has the biggest range of normal stress. Right? So when I put the two of those together, it's a very big number, and of course the light is down by a factor of 10. And that's actually that's what we see in the experiments. And then finally, you can do a cycle of tension followed by a cycle of torsion, and here we see nothing happens. And here's the tension cycle, and here's followed by the torsion cycle. So the key to non-proportional loading really is to understand how the external loads here combine to produce stresses on an element of the material, and then we have to search this element of material to find what is the critical combination. What is the critical combination? And if you haven't done it before, it's impossible to guess. It's impossible to guess. So let's go on a little bit. And look at the idea of non-proportional hardening. And this is something that only happens in multi-axial fatigue. So again, I have the in-phase and out-of-phase loading, easy enough. And I do this with sine waves. And I want to take a tube, and I want to take this tube, and I want to load this with combined tension and with combined torsion, either in-phase or out-of-phase. And the next three slides I want to draw on the same scale. And so as I am cycling this, then I cycle this and I measure the stress-strain response both in tension and in torsion. And if I do that, here is the response in tension, fine, and here is the response in torsion. Let's do the tests now, and let's cycle this out of phase and record the same behavior. And this is what you get. Same strain ranges. And you will immediately notice the magnitude of the stresses. The first thing that you notice is that the hysteresis loops are not of the standard shape. Instead of being pointed at the ends, then of course they have these rounded ends and they look like that. That's a consequence of the coupling matrix and all the plasticity that I showed you. Look at the change in magnitude. Right? Same strain ranges. No difference. Look at the change in magnitude. Right? What would happen to the fatigue life of something if I doubled the stresses somehow? So if I double the stresses, how much will the fatigue life change? All of you can work this. 2 2 to what power? Right? 2 to the power of the slope of an SN curve. Right? Easy. Very fun to be on PhD, asking these kinds of questions, right? What is the slope of an SN curve? What would you like? How much? 0.2, right? So 5th power. It's easier for me to work with the reciprocal. 5th power, 2 to the 5th power. How much is 2 to the 5th power? Okay, hard way. 2, 4, 8, 16, 32. You all should know this because you are of the digital generation. You all think 32 is a round number. You know, I'm in the slide rule generation. 50 is a round number, not 32, but you know, 32 is in the new digital generation and a nice round number. 2 to the 5th. So I expect if I could double the stresses, that I might change the fatigue life by a factor of 30. Huh? Does that make sense? Right? Because remember Morrow's ideas, right? You know, I can strain something, but the material's resistance builds up a lot of stress, and both the stress and the strain must contribute. So if I do something to the material that can double the stresses, right, that must be more damaging. And we just went through a quick exercise to say that difference should be about 30. Okay? Well, let's see. There's the behavior, right, on the critical plane for the in-phase loading. There's the behavior on the critical plane for the out-of-phase loading, same strain range. And we can see that we run a series of tests at a high stress, and so the lifetime here is about 38,000 cycles. And if we take the same and we do this in the out-of-phase loading, that the lifetime was reduced by a factor of 10. Not bad a prediction for our simple model, was it? Right, our simple model said maybe we would expect a factor of 30 difference, and we go in the lab and say, yes, it was a factor of 10. Right? I think that's very good. Right? Very good. Right? Because I expect a big effect and I see it. And by the way, if we do it in the lower stress level, of course, if we go to a lower level, then the lifetime is longer, of course, at a lower level, but we compare the value of 310,000 with the value of about 40,000. And so, you know, again, our factor of 10.